Hello, everybody, and thanks for listening to this talk on the design of consequential ranking algorithms. My name is Behzad, and this is a joint work with Vicenç Gómez, Abir, Bernhard Schölkopf, and Manuel Gómez Rodriguez. Ranking systems have known to promote unreliable contents in recent years on the web. Ranking algorithms often promote information that are unreliable, polarizing, inaccurate, manipulative, and fraudulent. These problems have long-term negative impacts for the society and monetary and mental costs for individuals. Take this as an example. In the past German election, someone on Twitter posted the following tweet. I'm a poll worker. On Sunday, the day of the election, I will invalidate the AfD votes. AfD is a political party in Germany. This tweet gathered a lot of attention and became viral. Ranking algorithms also rewarded the immediate popularity and made sure that this tweet reaches millions of people. Later on, the German government issued a clarification indicating that poll fraud is punishable, and later investigations also showed that the claims in the tweet were in fact false. However, by then, the ranking algorithms plus the network effects meant that the original tweet had reached millions of people without them ever knowing about the clarifications and the investigations. This created anxiety throughout the society and cast doubts over the integrity of elections. Rewarding short-term popularity by ranking systems leads to a spread of misinformation over the long term. In this work, we provide a unifying framework for modeling user dynamics and ranking algorithms to achieve and create new ranking algorithms that account for the long-term behaviors and long-term consequences of their rankings, while also trying to maintain similar results to the default or original rankings that exist today. To start with, we start modeling ranking and user dynamics. We adopt the framework of Markov decision processes by first modeling content such as tweets as represented through a feature matrix X. For each tweet, we represent it using a feature vector, and that tweet may contain information such as number of shares, likes, reactions, and so on, while also for every tweet, we represent at every time step a ranking where that tweet appears on the feed. Then, according to the Markov decision process, we assume this process continues at several time steps. So at time step 1, we assume that the feature matrices gets changed and updated according to the rankings and the previous feature matrix. At the same time, the new rankings are generated based on the same on the feature matrix, and then there is a cost function that computes the potential cost to the welfare as defined by spread of misinformation or similar such criteria that we care about. We also consider a default or original ranking algorithm working in this scenario, represented as P0 given y and given x. P0 for y given x. This ranking algorithm can be any default or already existing ranking algorithm that we will modify to create the new consequential ranking algorithms. Next, we define the problem of finding out consequential ranking algorithms. For this, we define the following minimization problem, in which we define a cost function averaged over several trajectories drawn from a particular consequential ranking algorithm denoted by p theta. The cost function s theta is defined to capture the cost to welfare over the entire trajectory tau, plus a controlled parameter lambda that trades off another term with fidelity that represents fidelity between original and consequential ranking and the cost to welfare. Finally, we represent the induced trajectory of tau over the observed data by the following joint distribution over ranking model and user dynamics at the bottom of this slide. As it turns out, this minimization problem has a very simple solution that can be described analytically. The solution, as it turns out, allows for a very simple sampling method in which we can draw samples from the original ranking, weighing them according to the specific terms that depend on the cost to welfare and the user dynamics, which in turn gives us the consequential sample from the consequential ranking. However, in practice, these sampling methods are inefficient and have high variance, and therefore we propose a second solution or second method to compute optimal consequential rankings using a stochastic gradient-based algorithm. We leave the details of the derivation for this method to the interested reader to consult with the paper. We only note that to estimate the updates, we use the log derivative trick plus the Monte Carlo samples to estimate gradients of expectation of the loss. In our own experiments, we use a specific parameterized ranking model called Planck loose ranking models, and we apply our model to a set of experiments as we discuss here. First, we start with the synthetic experiment in which we simulate a social setting in which posts are represented with a number of shares, AT, and a score of misinformation score. Each post is generated by some simulated user over 20 time steps, and the feed is assumed to have 4 posts in it. We also assume a utility function as represented as computed by a Kendall-Tau correlation between the ranking YT and ordering induced by number of shares AT. The cost function also is defined as the number of misinformation posts on the top with indicator drawn according to the indicator of whether a post is misinformation or not, drawn according to the distribution of misinformation score in the feature vector. On the right, you can see the results on the synthetic experiment, in which we consider a bracket of utility values that resemble low correlation with the number of shares AT. In this scenario, the optimal ranking and the optimal gradient-based ranking provide a lower cost compared to the optimal greedy baseline, in which we try to only push the posts with the misinformation score higher than a threshold down. And the original ranking is represented with a dashed line. We also provide the results for different brackets of utility with the low correlation and the high correlation. For the high correlation, we can see that the optimal ranking, in fact, achieves a lower cost compared to the other two baselines, and the optimal gradient-based solution achieves a better result compared to the greedy baseline. We also apply our framework to the Reddit dataset. In this setup, we collect data from Reddit platform in which every thread contains several posts, and every post is represented by the number of posts that preceded that post, and also an unreliability score gamma. On average, every thread has about 21 comments. So the length of the trajectories that we consider for our framework would be about 21 steps on average, with 5 comments on being the length of the feed. We also use the Kendall-Tau correlation between the ranking YT, but this time the correlation is computed between the inverse chronological ordering and YT. We also use the cost function as the unreliable post on the top of the feed, similar to the previous synthetic experiment. And as you can see on the right side, you can see the original ranking appearing on the top right, with the optimal ranking and the greedy baseline appearing with the blue and red lines on the plot. The optimal ranking, as you can see, achieves a lower cost for any specific values of the utility. So if you want to achieve a specific utility or a correlation value, we can always achieve a lower cost with the optimal ranking. With this, I would like to conclude this talk. Since we worked on this paper, we started a startup called Reasonal, in which we are improving the reliability of information on the web. We invite you to check out our website on https://reason.al, join our mailing list, check out our browser extension, check out the Twitter spot checker that we have. Thank you very much.